Alright, in this video we'll be looking at what is called the Micheal reaction, which is the reaction of enolates with alpha, beta, unsaturated carbonyls. So if we look at an alpha-beta unsaturated carbonyl, and again, here's our alpha carbon and our beta carbon, that can form a couple resonance structures where we do charge separation. So they're not great resonance structures, but they are legitimate. We can put a positive charge here and a negative charge there. We can move the electrons from this double bond over. And we can put a positive charge on the beta carbon. And so both of these sites are considered nucleophilic. So electrons can attack either this carbon or the beta carbon. And so we can have, you see that there are two sites, and this leads to two types of addition. And the first is what we call simple addition. And that is addition to the carbonyl carbon. And an example of that so we'll take this alpha-beta unsaturated ketone. We'll react that with methyl magnesium bromide, and this will attack the carbonyl carbon. Let me color code it. And then with an acidic aqueous workup, we can protonate that oxygen and form the alcohol. And so strong nucleophiles will attack at the carbonyl carbon. They include organometallics, such as Grignard reagents or organolithiums, and hydride ions will also attack at the carbonyl carbon. So they'll prefer to attack here rather than at the beta carbon. So the other type of addition that we can have is what's called conjugate addition. And this will be favored by weaker nucleophiles. That includes organocuprates, which is a carbon-copper compound, hydroxide ion, alkoxide ion, amines, enolates, enols, cyanide ion. And an example, we'll start with this cyclic ketone. React that with LDA at negative 78C to form the enolate. Then we'll react that with an alpha beta unsaturated ketone, followed by an aqueous acidic workup. And we wind up with this product, and we call that Micheal Addition. So, since this is number 2, not number 1. But this conjugate addition to the alpha-beta unsaturated carbonyls is also referred to as a Micheal addition or Micheal reaction. So let's take a look at the mechanism for this real quick. That we'll start with the enolate. And we'll have our alpha-beta unsaturated ketone. The electrons can come down. That'll force this double bond to attack the other double bond. The electrons will move over and up. So we'll reform this carbonyl here, and now we have a similar to an enolate. This enolate, I've switched my colors. That when we do the aqueous workup, the electrons will come down, and that double bond will attack a proton to protonate the alpha carbon, forming our final product. And so that's the mechanism that we still form an enolate or an enol. That enolate can attack the double bond of an alpha-beta unsaturated carbonyl, and that'll form another enolate. We protonate that enolate to form a diketone in this case. So let's look at a couple more examples. That we'll start with our alpha-beta unsaturated ketone, and rather than reacting it with an enolate, we'll choose another weaker nucleophile, an organocuprate. So here we have two ethyl groups attached to this copper with a lithium, and we'll follow that up with acidic aqueous workup, and I can color code this too. And we'll end up that this carbon will act as our nucleophile to attack this carbon on the end of our ketone, and we'll wind up with let me count these real quick. 1, 2, 3, 4. 1, 2, 3, 4 plus 1, 2. Yeah, I think that's correct. We'll wind up with this final product, and we'll go through this intermediate and so after protonation, we'll wind up here. And so essentially the electrons from this carbon, because these organometallics tend to act like carbanions, and so we can pretend like there's a negative charge here that will attack this terminal double bond carbon, the beta unsaturated carbon, kick the electrons over and up, forming this product, and then we'll draw in our proton. The electrons can come down and pick up that proton to form our Micheal addition product. Now, if we do this slightly differently, let's say instead of doing an acidic aqueous workup in step 2, that we add come on, draw. Anyway, methyl iodide as our second step. So the first step will be the same. In fact, I should have left that up. That we'll wind up with this enolate. But now, because we haven't added acid, there are no protons around to protonate. Our only option is to attack that methyl iodide. And so the electrons can come down, attack that methyl, kick off that iodine, and our final product will have a methyl group at the alpha carbon rather than a proton at the alpha carbon. And so we can use this for alkylation as well. Instead of just protonation, we can add two groups, two alkyl groups to our compound in essentially the same reaction. So let's look at another one. We'll start with this beta keto ester. We'll use LDA at -78C. It'll pull off one of these alpha protons here in the middle. And then we'll add I've made this too large. I'm running out of room. Let me shrink it down a bit. Then we will add our alpha-beta unsaturated ketone, followed by acid and heat. And what product will we end up with? Let's see how to color code this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I'll count the carbons later to make sure that that's correct. So how do we end up with this product? Well, essentially, once we get this enolate, that enolate, the electrons can come down. These electrons can attack that double bond, kick the electrons up to this oxygen. So we would form essentially this product. That enolate would attack our alpha beta unsaturated ketone, forming adding that ketone to that alpha carbon in the middle. Then when we do the acidic aqueous workup, we would hydrolyze this ester. So we would convert that ester to the carboxylic acid. And now we have a beta-keto acid, which is capable of decarboxylation. So we lose this CO2. We lose this group as CO2. And now let's count our carbons. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. I have added one too many. I think 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, I think that's correct now. So the last thing that we'll look at is related to the Micheal reaction. But it's a Robinson annulation. And it's essentially a Micheal addition plus aldol condensation. And so if we start with, let's choose a different color. We start with this ketone. We react this alpha beta unsaturated ketone in basic aqueous conditions and heat. We will wind up with this bicyclic conjugated alpha beta unsaturated ketone. I should point out at this point that the Micheal addition also works under basic conditions. We don't have to do this under acidic conditions. But anyway, we'll go through the mechanism to explain how we get from here to here, and I'll color code it so it makes more sense. That we start with our cyclic ketone. We have a hydroxyl group, or a hydroxide ion, that pulls off one of these alpha protons. Forming this enolate. The enolate can then attack our alpha beta unsaturated ketone. So we reform that carbonyl and we attach this enolate to the ketone. Then we protonate that enolate form this diketone. But now we have these alpha protons, and if we're still under basic conditions, and so hydroxide can come back around, pull off one of these protons, we'll form a different enolate, Now this enolate can attack this carbonyl And that's carbon 1, 2, 3, 4, 5, 6. So we form a 6-membered ring. The carbon 1 would be attached to carbon 6. So we'll draw our 6-membered ring. This would be 1, 2, 3, 4, 5, 6. Carbon 2 would have our ketone. Then we've got this alpha proton here. Well, before we worry about that alpha proton, let's protonate this. I'm running out of room again. Okay. So now we'll worry about this alpha proton, because hydroxide can come around, and through an E2 elimination reaction we can pull off that hydrogen, kick off that hydroxide, and form our final product. With our double bond and our ketone. And so that's kind of a complicated mechanism. We've got 1, 2, 3, 4, 5, 6, 7, 8 steps. But we start with the Micheal addition here, where the enolate attacks the unsaturated beta carbon, and we finish it up with the aldol condensation here, where we have an aldol, the ketone and the alcohol beta to each other. So we do the condensation or the dehydration reaction on this aldol to wind up with our alpha beta unsaturated cyclic ketone. So that's it for chapter 19.